In my last video, I went over the design and build out of a 16-bit memory module for my Breadboard TTL CPU inspired by Ben Eater's SAP1 project. Here you see the finished project, with the memory module integrated into the Breadboard CPU and a program running out of its memory. In this video, I'll go over how I got all of this working by integrating the memory module into the Breadboard CPU and creating the software needed to program it. In my last video, I said this project to build a 16-bit memory module was very educational for myself. There's a lot of things I had to learn in order to design the hardware and figure out how things interact with each other. That educational value continues into this value as I try to figure out all the software in order to make this module work within my Breadboard computer. However, before I get into that, if you have not watched my last video on the hardware design of the 16-bit memory module, go ahead and pause this video and watch it. I'll link it right here in the video. Now, once I integrated the hardware of the 16-bit memory module into my Breadboard computer, one of the first things I had to solve was the new microcode. The microcode is used to coordinate all the various pieces of a CPU in order so that they can act together in order to accomplish various instructions. And so with this new memory module, I had to come up with a new microcode. Then I need a way to enter the bytecode to be able to run programs on this computer. Now, in the original Ben Eater SAP1, entering the bytecode for a program was fairly straightforward. It only had 16 bytes of RAM, and so it was easy to be able to manually key in a program using the microswitches on the computer. Now, I did leave microswitches on this computer because of the reasons I discussed in my last video. However, now that I have 32K of RAM and 32K of ROM, manually keying in a program that makes substantial use of that memory space would be cumbersome, to say the least. And so one of my goals, as I recall from my last video, was to be able to program the ROM with a program, and be able to use as much of that ROM as necessary. So I needed a way to be able to not only compile any code that I have, but create an image that I then burn onto the ROM. On most CPUs, the way this is done is through something that's called an assembler. Basically something that takes a code, that assembly code, and compiles it into the actual byte code for the CPU. Now, my CPU does not have any assemblers built for it. And so I needed to find a way to kind of deal with that. I ended up building my own assembler, and I'll get into the details of what I did to make that happen. So in this video, I'll go over both how I built the microcode and the assembler and demonstrate how they work together in order to make a program work. All of the code and the schematics for the design of what I talk about in this video and my last video on this topic are available in my GitHub repository, which I'll link down below in the video's description. So let's cover the microcode needed to make this work. In previous builds, I had written a Python program that would let us to generate the necessary microcode for any given instruction set that I was trying to implement. The problem was that each time I wanted to create a new instruction set, for example, when I implemented the increment registers, I had to duplicate the Python code and slightly alter it for the changed instructions. This got cumbersome, and it's actually a very bad coding practice. Really, what was changing from each instruction set to the next was the configuration of that instruction set. To me, this meant that ideally the instruction set should be modeled in a configuration file, and the Python code should generate microcode ROM based on that configuration file. So since the last project, I've created some more general microcode generation program that would take on the task of taking a configuration file that defines the instruction set and set what control lines what should be active for any given step in a given construction. So here is that microcode. I'm not going to go over this line by line, but I'm going to highlight some of the important details. First of all, this code, unlike the last code that you saw where I had to model individual control lines and what bits were active for any given control line, this one has no such configuration. All of that configuration actually comes in a configuration file that I implement elsewhere. For example, the configuration file for this update is right here. If you're not familiar with what this configuration file format is, it's something called YAML, yet another markup language. It's a very easy to use configuration format to be able to configure whatever you want. And so I use that for this program, and it's pretty straightforward to use. The first block is just the file name of the output file where the binary image that you're going to create is going to be written to. The second block is the control lines that are going to be active in this ROM configuration or microcode configuration. Here I define the names of the control lines. These names are just used for human readable purposes. The number associated with the control line is actually the control line position from left to right in my expanded control line setup, which I talked about in a previous video. So basically each control line has a number, and I assign those numbers to a name for that control line, and I use those names later down here where I actually define the control lines that are active for any given step. This instruction prefix block, it just defines the set of steps that happen before or at the start of every single instruction that I'm going to be creating. There could be no steps, like every instruction is unique, or there could be a step that sets up the instruction itself. As you recall, in the Ben Eater SAP1 project, it actually had 2 steps at the beginning that every single instruction had, which was all about taking the next instruction out of RAM and placing it into an instruction register. The same thing is happening here, and what this first step actually does is take the instruction out of RAM and places it into the instruction register. However, because this new architecture actually has the address bus separate from the data bus, we can actually do this in all one step. So the first step is to actually set the program counter to activate, and that is write its value to the address bus. Then tell RAM, which is now set to the value that's in the address bus, to export its value to the data bus. Then tell the instruction register to read it in. And all while this happens, also increment the program counter to make it point at the next byte of memory. Then we go into each one of these various instructions. I'm not going to go over every one of these instructions. You can actually look at the details of this in my GitHub repository, but I'll very quickly go over the load A instruction, something that we did cover in the last video. How this manifests in the control lines is, the first step after the prefix step is basically to take the memory address that is actually following the instruction in RAM. So the program counter, after it was incremented after it loaded the instruction into the instruction register, the program counter is now pointing at the lower byte of that memory address at which the value that we want to load into A resides. And so the next 2 steps are all about taking the value out of RAM, that memory address value out of RAM, and putting it into the memory address register so that we can then grab the value that we want to load into the A. So this first step basically activates the program counter, which then tells RAM to output its value onto the data bus, and then address register reads in that value. Now you notice that the high-low control line is not active, so that implies that we're loading the value into the lower byte of the address register. We also increment the program counter in order to get to the next byte of the address in this instruction. So this next step is all about reading that next byte into the high value of the address register. It looks very similar to the previous step, except the high-low control line is now active, and we don't need to increment the program counter again yet, so we're not going to go into in this step. The final step is actually doing something useful. Now activates the address register onto the address bus, which then causes RAM to be writing the value that we actually want to load into the A register to the data bus, and then we tell the A register to read that value in. We also go ahead and increment the program counter, so now it's pointing at the next instruction that the next step is going to actually load. The final step of this instruction is just to simply reset the step counter so that we can start the next instruction that is going to be loaded, and the whole cycle starts over again. Now that has been explained, let's go ahead and burn the microcode into ROMs and move it on to the next step to get things working. Okay, the first step in order to create the microcode ROM is that we actually have to create the image from the microcode generator that I just discussed. To do that, the step to do that is basically to run the Python program, which is written in Python 3, which is also located in the microcode generator folder within my repository. So let's go ahead and run this program. Generate microcode. And what it takes as an argument is the configuration file, which I just showed you, which is right there. Now, we go ahead and run it, and it runs pretty quick. And now you can see that the binary file is generated. So the next step is to actually burn these microcode ROMs with this image and get things turned on. So let's go ahead and do that. The first step is to take out the images, the ROMs. Put them in the burner. And then MiniPro. And that's the command we want. I always forget what is the option for specifying the device. It's -P, so I have to look at a previous one. And the image that we want to burn is this upgraded RAM 4-bit. Okay, so there we go. Let's go ahead and burn that. And do this for all of the ROMs. Okay, now that we have the control line ROMs all set up, the next step is actually to create a program to make that work. Now, the problem that we need to solve is how do we actually get a program into the system? Right now, I have both a ROM and a RAM chip on here. However, the problem is when I boot up this computer, the program counter here is going to be reset to point at an address of 0. And the address of 0 is actually the ROM rather than the RAM. So if I wanted to key in a program into the RAM, that's my problem. The program counter is going to boot up pointing at the ROM. So we need to put something in ROM, and it's a really simple way to kind of get things started is to have the first instruction in ROM actually jump to the first byte in RAM, which is hex 8000, and that way I can key in the program at a hex 8000 and get things running. So let's actually do that. Let's actually put a really simple program into ROM, which jumps straight to hex 8000. And that will allow me to key anything into RAM using the micro switches here on the computer. So one way to do that is we're going to have to create a binary image that has this value in it. And that binary image basically needs to be 32K in size because I can't burn a 32K ROM with anything smaller or larger than a 32K binary image. So one way to create that binary image, so let's actually go here to my boot code directory and do that work here. Actually, I already made it before, so let's go ahead and try it again. So the way to do that here is we're going to use the command dd, which is like disk duplicate. And the way the command works is that it reads from something and reads it from a source and then writes it to a actual file or destination. And the source we're going to actually read from is something called /dev/0. And basically what the source is just nothing but zeros. And so basically that's what we're going to do is write a bunch of zeros into a binary image and then reset a few of the bytes to the actual instructions. The output is going to be the binary image file that I want to create, and I'm going to call that test.bin. And then the size, which is what the BS option stands for, is going to be 32 bytes, or 32K bytes in size, which is 32768. And finally, an count option of 1, and then that very quickly creates a test file. So if you actually look at the files that we have here, you will see that this test bin image that I just created has 32K bytes, which is great. But the problem is it's filled with zeros, and I need to change some of the bytes in order to have that jump instruction at the beginning. One way to do that is to use a program called hexedit. If you're using a Mac, it's really easy to install. You just use Homebrew with a brew install hex edit. If you're using Linux, you probably use whatever your package installer your favorite package installer that you use, and do the same thing. If you're using Windows, admittedly I can't help you there because I don't really know Windows, so you'll have to figure that out yourself. But anyways, you use this program and we can very easily edit the binary file we just created. You open up this program, you see there's nothing but zeros as we described. Now, the first byte that we need is to be the jump instruction. And in the 4-bit instruction set that I just burned into the microcode, the jump instruction is actually the value of 6. Now recall that I'm still using the 4-bit instructions of the original Eater SAP1, and if you really look at the format of the instruction byte that actually gets loaded in the instruction register, the instruction value actually resides in the upper 4 bits of the instruction byte, because in the original Eater SAP1, the lower 4 bits was the address or direct value that was going to be operated on. So here I need to put that value 6 in the upper 4 bits of the instruction byte. Now the next 2 bytes that are going to be in the file are actually the address that we're going to jump to. You remember I said we're going to jump to hex 8000, which is the start of RAM. Now the way to enter it here, you might think you want to put it in as 8000, but I did set up this computer to be in the little endian format. The reason for that is to make some of the future work that I want to do around updating the ALU to be able to handle larger values than 8-bit values. It makes it a little bit easier if you work in little endian. So what the little endian does is just swaps those 2 bytes, and so the lower byte, which is 00, will be in the first byte after the instruction, and the upper byte, which is 80, will be in the second byte. So this is what we're going to edit it to. The first byte being the instruction, and the next 2 bytes being the address that we're going to jump to in little endian format. So we go ahead and save that with a Control X. Yes, I want to change, and now the file is saved. And now we can burn this file to the ROM here on the memory unit. So let's go ahead and pull that ROM out, and then going to burn it. And the file name that I'm going to burn it is that test.bin. There we go. Okay, burned. Let's put it back into place. There we go. Now, let's go ahead and test this out. Get my computer out of the way. Now that my computer's out of the way, let's go ahead and power this up. And you see that the program or the computer comes up in some random state, right? I'm going to stop the clock, reset it so the program counter points at 0. Now remember, at the address 0 is the jump instruction, which we see already being outputted from RAM. Hasn't been loaded in the instruction register yet. That's what will happen when the first clock tick, but we're already there. So things are looking good. So let's go ahead and turn on the clock, and we see once it jumped to the RAM address, there's a bunch of junk in RAM, so it basically did something random and came up to a number that looks like a halt instruction, and everything came to a stop. So I want to program an actual usable program into this. So I'm going to stop the clock, put it into program mode, and reset things. The program I want to enter in is this program here, which is just a simple summation loop. This is actually using the assembler that I'm going to be talking about next, so I'm not going to go over the details how I produced it, but the output should be fairly self-explanatory. I have a bunch of instructions here that represent the loop, that program that I'm going to implement, and those instructions have been turned into bytecode, and here's the corresponding addresses where that bytecode should resolve, and I also output the binary to make it easy to kind of key it in. So let's go ahead and enter this into the computer. So the first thing I need to do is set the address to 8000, hex 8000 that is, and I'm going to be entering in a value of 5. The first step here, yeah, it's already 5. So let's go ahead and burn that in. What that first step does is set the A register to 0, so that it just initialize everything. I'm going to burn in the rest of it. I'm going to key in the rest of these things. So here I go. 8001. I want a value of 0. And this last byte here is actually a variable, which is the byte value, or the actual value that we're going to be counting by. I'm going to start off by counting by 1, which is what I actually have in this code here. So in this last byte, we're just going to enter the value of 1, and that will set what everything's going to be incremented by. So let's go ahead and make sure everything's reset again. The clock is off. Let's go back into run mode. Turn on the clock and see if this works. There we go. Looks like we are counting by ones. So I would claim that to be a success. You know, this memory module is working. It's integrated well with the rest of the computer, and I have a working program. However, you know, as I mentioned earlier, this is not everything I was trying to accomplish. You know, I manually created a ROM image here in order to kind of boot the code into RAM so I can key in a RAM program. However, as I stated in my last video, my goal is to be able to create, you know, more complex programs in ROM and run codes out of ROM. The next step here is actually to create an assembler that will allow me to do that. So let's cover that now. So the assembler I created is here on my GitHub page. I call this assembler Bespoke ASM. The reason why I call that is that because it allows me to customize the instruction set that would be generated by this assembler. The instructions on how to install this assembler, it's something that you can install on your computer, are basically right here. If you're familiar with Python and installing Python packages, that's exactly how this works. Now, to do that, I give instructions here. Basically, you'd want to create a Python virtual environment, clone the repository, and do a pip install. Once you have installed this and you have activated the virtual environment that you created for this, using the assembler is pretty straightforward. And here's the command to use it. Bespoke ASM, compile. You give it a configuration file of the instruction set, and then the code. Now here in this repository, I have actually documented things in this wiki. A more detailed page is provided on how to install and actually use the command line, including options like the option to pretty print the output, which is actually what you saw when in the previous part of this video where I was hand coding in a program that already generated. You can also control the size of the output binary file that is. And this is actually pretty useful when you're creating ROM images in a memory space that's split between ROM and RAM. In my case, ROM occupies the first 32K and RAM occupies this second 32K. When I write programs, I'm going to be using addresses in both ROM and RAM and possibly ideally, the reason why you're using the addresses in RAM is because you have variables there and blocks of data that you want to be operating on. However, when you burn the ROM images, those variables don't get burned into the ROM because they exist in RAM and you can't set the RAM. So this option here to set the binary max address kind of tells the program, even though I have written a program that uses addresses well into the upper 32K, approaching 64K, an address of 64K, only output the bytecode that up to the address of 32K so that I can create a binary image to burn the ROM. So that's what that option is used for. You can see that. You'll see that shortly when I actually start creating ROM. Also have created a page that gives the assembly language syntax. This is, details on the allowed syntax, the kind of numeric values you can specify, how instructions are formatted, the concept of labels and constants, which are fairly common in assembly, and the various directives that the assembler actually is able to understand. One directive that is actually pretty useful is this 0 until. Basically what this does is it fills the bytecode image with zeros up until a certain address. And the way that this would be used in creating a ROM image is you write all your code, a ROM starting at address 0, and you likely are not going to use the full 32K of the ROM space. And so at the end of your code, you'd put the 0 until, and then you put the 32K, so that the assembler will generate a bunch of zeros up until the address of 32K, thus filling the ROM image with something. Also allow data directive, which allows you to create data values in the bytecode. Here's some examples of how to do that. Even though it's what the byte directive actually means is that you're creating a piece of data that's sized at 1 byte at a time. And even though you can create multiple byte blobs of information from the compiler's perspective, each individual byte is addressed independently. The reason why this is important is if you supported like a 2-byte value and you're using little endian, the compiler would want to know that so it can arrange the bytes correctly in the bytecode. But since I'm not supporting 2-byte values here, only 1-byte value, that issue doesn't really matter too much. Here's an example of using this assembler in order to write a code. Now, this code here is for the original Ben Eater SAP1 breadboard CPU. So this will actually generate code that would run on that original computer. And I'm not going to go over this line by line, but you can kind of see the sense of what's going on. This is a kind of a count by loop again, but it counts by basically in increments all the way up to 255 using one increment value, and then once it gets to 255 it increments the increment value and starts over again, and it keeps on going through those loops of loops until everything gets reset. The last part of this wiki is to the actual instruction set configuration file. I go over a lot of details here. The configuration file is either a YAML file, kind of like the microcode generator. Also support JSON if you'd rather do this in JSON. It's the same general structure. And basically, this configuration file has a few important parts. First, a general part that kind of talks about the overall architecture of the system. Here you specify the address size for the address space that you are operating in. This is set up for the original Ben Eater SAP1. The address space there is 4 bits, so hence the reason I have 4. The endian there doesn't really matter much because you don't have values greater than a byte at any point in that architecture, but I go ahead and indicate that it's big endian just to be able to indicate something. Arguments, this concept of an argument config, it allows you to specify the type of arguments any given instruction is allowed to have. And here you can name the argument types. Here I call it one type an integer. That's not a keyword. That's actually just what I wanted to call this argument type. And I say it's a numeric that is not aligned, and its bit size is 4. Similarly, I have an address type, which is also configured. It's very similar, in fact, identically to the integer. I just separate them because it makes sense later on when I set up these various instructions. The instructions are configured by first indicating if it has any arguments. If it doesn't have the argument block, that means it doesn't have any arguments. And if it has arguments, what the argument type is. And the value you put here for the argument type is exactly what was put up here in the argument config. Then you describe the bytecode, what the value is and how many bits it is. And so what this ends up doing, what the assembler ends up doing, is when you have an instruction, it will take the bytecode of that instruction and then follow it up with the bytecode that would be generated for any of the argument values. And this configuration basically tells the assembler, what are those values to use when you see any given instruction. So that's the bespoke ASM. Before I go into its use, there's one thing I really need to call out, and that is there is actually another assembler out there called custom ASM, which you could use to create your own custom assembler, hence the name custom ASM, in order to generate bytecode for your custom CPU. This is actually a fairly robust and powerful assembler, and I could have gone ahead and used this for everything I needed. I chose not to because I wanted the learning experience of creating my own assembler. And so that's why I went down the path. But if you are interested in using a more robust assembler than my bespoke ASM, here's an option. I just wanted to point this out. This is a fairly good implementation. One of the details you should know is implemented in Rust, and so you actually have to install Rust on your computer before you can actually run this code itself. Finally, let's go ahead and actually use the assembler. The first thing I'm going to do is actually look at some code. I already have the assembler as a bespoke ASM installed in my computer. So let's go ahead and look at some code. So I am going to go into my repository. This is the RAM and ROM upgrade, and I have some examples here. I have a few examples. I'm going to go over the let's do the Fibonacci, because that is the popular one in the original ESP one. So let's go ahead and look at that, the Fibonacci example. So here it is. And you can see this one's fairly straightforward. The way I'm implementing it here, I'm actually taking advantage of the increment registers that I've implemented in a previous video in order to kind of count through the various values that I'm going to calculate in the Fibonacci for. If you haven't implemented my increment registers, you won't be able to run this program as configured, but it should be fairly straightforward to change it. So I'll leave that as an exercise to the viewer. The first step here is basically to initialize the display by setting the A register to 0 and outputting it to the display register. The next step is to store that 0 value into this variable that's at f_n, or Fibonacci of n, -1. And I want to emphasize something, and this is something that I find to be kind of convenient in the compiler, that really the label that is being used here is just this f_n, which is down here at the bottom, which I have defined it to be an individual byte. I've also, just prior to it, I've defined another variable being f_n_1, which is another byte. And as you recall from the Fibonacci sequence, in order to implement it in a loop version, you actually have two variables, basically the prior value of Fibonacci and the value prior to that of Fibonacci. And basically the Fibonacci value is the incremented Fibonacci value. It's just the sum of the prior two Fibonacci values. So you want to keep track of those. And that's what these variables are for. However, rather than addressing the f_n-1 directly, I go ahead and use a feature of the bespoke ASM I implemented, which is basically expressions. What this does is it will take the address of f_n and subtract 1 from it, and then use that as the address that this sta command is going to be storing the A register to. Now, it so happens that that address ends up being the byte before f_1, which is this f_n_1. But, I thought it was interesting to just use this expression rather than using that label. The next command is to set the A register to A, and then to load that into the f_n. The reason for that is now I've initialized the first two Fibonacci values, and I can start the loop. The next step is to initialize my counter, which is the I register, and I have a max n value that I have defined that is actually defined right here. A byte value is a 12. We load that into the I register. The maximum value of Fibonacci that you can actually calculate before you start overflowing is 13. However, I implement the value of 12 because my loop is starting at a value of 0, so it's the count base 0 kind of issue when you're doing loops. Okay, now that everything's initialized, then we start the loop, and basically it's a summation loop. I load the N value, I store it into a temp value because I'm going to have to do a value swap later. I add to the Fn value that's in the A register, the Fn-1 value. Then I store that in Fn. I output it to display so that you can see the Fibonacci value increasing. Then I save that, I load that temp value that I previously say into A, so then I can write it into the Fn-1 position. Then I decrement the I register, that's my counter again. I check to see if the counter has reached 0. If it has reached 0, I jump to the end of this program, which at the end of the program, it just jumps back to init and restarts everything. If we're not at 0 yet, I jump back to start and I do the next Fibonacci number. So that's the program. Let's go ahead and compile it and then burn the image. Now, to compile it, I actually have to activate my virtual environment. So to do that, I have the source. It's in the CPU1, my virtual environments folder, Breadboard CPU, bin activate. Okay, so that activates my virtual environment where I have the bespoke ASM compiler installed. And to run it, let's actually kind of look at the commands first of bespoke ASM compile, and we're going to enter -h for help, kind of see what options we have. I wrote it wrong. It actually wants the full option. So here are the options, the various things I have to set. I have to set a config file. I can optionally specify the output file. If I don't actually specify the output file, it's just going to take the source file and change this extension to .bin, and that's what I'll write to. We're going to have to set the binary max address. I talked about it previously in order to get the right size for the ROM image. And then we're going to have to print it out with printy print so we can actually see the output. So let's go ahead and do that. Bespoke ASM compile. And I kind of want to have set my configuration file, which is in my examples, and that's my configuration file. You can find it in the GitHub repository if you want to take a look at it. I also want to set the maximum binary address to 32768. Basically, I want 32K for the image. I want to pretty print it so we can actually look at the output, pretty print. And then the input is going to be my Fibonacci.asm. The output is going to be written to Fibonacci.bin. So let's go ahead and run that. Okay. The output was printed. Now, there's a lot there. I probably should have piped that to a less. So let's go ahead and redo this and pipe this to less so that we can expect what's going on in the output. Okay, so here's the program. Here's the instructions that we discussed again and them being converted into bytecode. You can expect that as you want. Now you see here after the last value that I want in a ROM, I have this 0 on 2 that I talked about previously, and it's going to basically zero everything up to address 7FFF, which is the last byte of ROM. So that's exactly what happens here. And let's kind of go to the end. And you see what happens after ROM is I have my variables that I wanted to place into RAM. You don't want to place variables that you're going to change in ROM because you can't actually change them then. To do that, once all these zeros have been written to 7FFF, the next address that anything is going to be assigned to is going to be 8000, which is the first byte in RAM. So the Fn_1 is going to be at address 8000, the F_n is going to be at address 8001, and the temp value that I talked about earlier is 8002. I placed this .org command in place, and what this does is actually tells the compiler to reset the address counter that it's using to keep track of where things are to 8000 so that everything following it is at 8000. Now admittedly that 0 on 2 7FFF actually accomplishes basically the same thing, but I just put both in to be pedantic. So that's what's actually written to ROM. Let's go ahead and burn it into the ROM image and see what we get. Let's take the power off before I do this, and take the ROM out. are going to burn the Fibonacci program that we just implemented, Fibonacci bin. I set the file size to the wrong size, so let's reset that to 767. That's right, 32K, but the last address is 32767 because that's 7FFFF. So my mistake. Okay, this is already outputted. The file has been updated, so let's now burn that to the ROM. Okay, it's been burned to ROM. Let's put this in place. And get my computer out of the way. And let's apply power, see if this works. Let's stop the clock, reset everything so that the program counter is pointing at 0 where the program actually begins. Restart the clock. Let's see what happens. Looks to be doing something sensible. There's our first Fibonacci number. There's our second Fibonacci number. There's our third. There's our fourth. And the numbers just get bigger from there. So there you have it. This 16-bit memory module that I started in part 1 of this video series has fully been integrated into my breadboard CPU, and I have created a tool chain around it to be able to generate both the microcode and assemble machine code for running programs. As I said, you can find all the details and designs and documentation for everything I mentioned in this video and my last video in my GitHub repository, and the links to that are in the to these repositories in the video description below. I have been asked by several people, what comes next? What are you building to? First and foremost, what I'm doing here is learning about how CPUs are designed and operated. I am doing that by working through building out of various components of the CPU, and I'm doing it iteratively. Like I'm taking little steps at a time, trying to learn a new concept. For example, this video is about learning about how to expand the memory module and all the implications of that, and how I had to add an address bus and I needed to create an assembler. That was all a learning experience. But in order to focus my efforts, I am trying to build towards something. You'll recall in my video about these increment registers here, one of the things I talked about was using the program or the algorithm of factorial in order to kind of test out whether things are working well. And so I'm building towards that. In that program, in that video, I actually calculated the factorial of an 8-bit number. And the largest factorial that I can calculate in an 8-bit computer where the results are 8-bit are 120. My goal is actually to be able to calculate the factorial of a 64-bit number, or actually have a result that fully fits into the 64-bit number regime. To do that, I'm going to have to do a lot of different things, beyond what I've just done here. I'm going to have to add a stack pointer so I can create subroutines and be able to iteratively or recursively call various parts of my code. I'm going to have to create a method to output larger values than 8-bit values. Right now, this display register here can only display an 8-bit result. If I'm going to calculate a 64-bit factorial, I need a way to display a 64-bit number. I'm also going to need to update the arithmetic logic unit to be able to handle something called add with carry. That is, if I'm going to add multi-byte numbers, like add a 64-bit number to a 64-bit number and have an 8-bit arithmetic logic unit, I'm going to have to add those two numbers in multiple steps. And one of the things you need to do is to literally carry the carry bit from one addition operation to the next addition operation for a higher byte in order to fully calculate what you're trying to calculate. So I need to update the arithmetic logic unit to be able to do that. There's a few other minor things that I need to do, and I'm going to be working through that in my future videos. If you're interested in seeing how all of this plays out unto the point where I am able to calculate factorial on this breadboard computer for values larger than 8-bit, approaching 64-bit, if not larger, go ahead and subscribe to my channel right now. I'll tell you up front, these videos are going to be slow coming. I do this part-time. I do it for fun. That doesn't mean it happens. I'm not going to have a video every week. But if you subscribe, when I do have the video, you'll get that notification and you'll see what I produce next. The other thing to do is to go to my GitHub repository and star that, or follow that repository. As I develop things, I'll be pushing it to my GitHub repository, again, which the link is down in the description below, and you'll be able to get notifications on GitHub whenever I come up with new designs or update my documentation or anything. And generally, the GitHub information is going to be updated before I actually make a video, so you'll actually get a preview of the next video I'm going to be making. If you like this video, please like it. Please comment below any questions you might have, or if you see any opportunities to improve. For example, if you think I did something inefficiently, please tell me. This is my learning process. I'm not in any way pretending that I know what I'm doing here, other than what I've talked about here for sure. But if you think I could have done it better, or I made a mistake, I'd love to hear your perspective. Please put your comments below. Tell me what you think. That's all for today. I hope you enjoyed this video, and I look forward to being able to share more with you in the future. Goodbye.